Hi there. For the purpose of this project, we would be presenting a study on smart home IoT products and the protocols used by these devices. Our selected range of protocols for the purpose of this project are Zigbee, Z-Wave, TCP, UDP, HTTP, and DNS. You might be familiar with some of these, and we would be introducing the others during the course of this video. As a team, we collectively owned a lot of these products in our homes and thus showcased our findings here. These products include Amazon Alexa, Google Home Ring, Google Nest Thermostat, iRobot Roomba, and the Philips Hue lightning bulbs.
IoT stands for Internet of Things, and as we explore smart home IoT product protocols, we need to understand how these IoT products connect with the Internet. This is where we come to the IoT operational models. There are three main models on how IoT products can connect with the Internet. The most common model is the direct model, and this is what all of our products that we mentioned use. This is where users communicate directly with the IoT device through a mobile app. Another IoT operational model is the transit model, and this is where IoT devices that can't exchange data with the internet server use Bluetooth or NFC. For example, Fitbit does this with Bluetooth. The third IoT operational model is the external server model. This is where the IoT device only exchanges data with external server, and the user can only retrieve relevant data from the server directly.
Z-Wave is a smart home communication protocol that uses radio frequency of 800 to 900 megahertz, which changes according to the country you're in, to monitor, control, and update status of household applications. It supports full mesh networks, so it allows for simultaneous communication between devices. There are 5 different protocol stack layers, which are the physical layer, MAC layer, transport layer, network layer, and application layer. The physical layer assigns radio frequency profile to Z-Wave physical channel, activates and deactivates radio frequency transceivers, manages transmission and reception of data frames, clears channel assessment, selects the radio frequency, and links quality check based on received frames. The MAC layer has a unique network ID number, which is called the home ID, and up to 232 nodes in one network. It also has a collision avoidance and backup algorithm with automatic retransmission for reliable data transfer and support for low-power operation via dedicated wake-up patterns. The transport layer handles retransmission, packet acknowledgement, the wake-up of low-power network nodes, and authentication of packet origin. There are 4 different frame types, which are singlecast, ACK, multicast, and broadcast. The network layer handles the transmission of a frame with correct repeater list, scanning of network topology, and maintenance of routing table in the controller. Lastly, the application layer is responsible for decoding and execution of commands in a Z-Wave network. The frame format used in the application layer is consistent of single or multicast, broadcast frame header, application command class, application command, and command parameter of 1 to X. The Z-Wave frame structure is shown here, which consists of the formatting of the application frame, the transport frame and its variations, and the physical and MAC frame. Zigbee is another smart home communication protocol that uses mesh networks and radio frequency of 2.4 GHz to monitor, control, and update status of household applications. Zigbee network is comprised of coordinator, routers, and end devices. Once the first coordinator is installed, it starts a new personal area network to allow routers and end devices to join the network. The coordinator is responsible for selecting the channel and PAN ID and assists in routing the data through the mesh network and allows join requests from routers and end receivers. When forming the Zigbee network, the coordinator searches for a suitable radio frequency channel, which is usable and not interfering with wireless LAN frequencies in use. This is because wireless LAN also operates in the same 2.4 GHz bands. Next, the coordinator starts the network by assigning a PAN ID to the network. Assignment is done in 2 ways. One is manual, which is pre-configured, and the other is dynamic, which is obtained by checking other PAN IDs of networks already in the operation nearby so that PAN ID does not conflict with other networks. At this point, the coordinator assigns a network address to itself and has completed its configuration, ready to accept network join request queries from routers and end devices to join the PAN. In addition, the coordinator sends broadcast beacon request frames on the remaining quiet channels, which is also referred to as beacon or PAN scan, to receive PAN ID of routers and end devices present nearby. The Zigbee protocol stack consists of the physical layer, MAC layer, network and security layer, and the application layer. The physical layer operates in the ISM band or 868 MHz band in Europe. It provides data transmission and reception, modulation of outgoing signals and demodulation of incoming signals, and it manages the function of the transceiver. The MAC layer frame is composed of MAC header, MAC payload, and FCS. It performs functions such as transferring data to and from the network and physical layer, association and disassociation of end devices, offer optional guarantee time slot for each device accessing the network and the coordinator, generate the beacon frame in the coordinator, security, and provide carrier-sense multiple access with collision avoidance. The network and security layer uses ad hoc on-demand distance vector routing protocol, or AODV, which is a reactive protocol, meaning the routes are created only when they are needed. It uses traditional routing tables, one entry per destination, and sequence numbers to determine whether routing information is up to date and to prevent routing loops. The application layer consists of application support sublayer, the Zigbee device objects, and
Philip Hue light bulbs are smart light bulbs that use the Zigbee protocol. This diagram shows how these lights work. From the mobile app, the user can request changes to the bulbs, which is sent to the Ethernet-enabled Philip Hue bridge. This is a physical bridge that is installed in the smart home. Up to 50 Philip Hue light bulbs can be configured to the bridge. The bridge uses the Zigbee protocol to send signals to the bulb. There are 5 main use cases for the Philip Hue light bulbs. Users can turn it on and off, specific light bulbs, adjust light intensity, adjust light colors and combination of colors, and set schedules based on the time of the day for the lights to configure to a specific setting. Also, there is an IFTTT, if this then that integration, which allows for users to customize routines within their smart home. For example, an IFTTT routine can be built so that the invocation Alexa, party mode, can trigger the Philip Hues to turn purple and a smart speaker to start playing a turn-up playlist on Spotify. This table compares the Zigbee versus Z-Wave protocols versus Wi-Fi. In terms of the range, both Z-Wave and Wi-Fi have about a maximum range of 100 meters. In megabits per second, it's clear that Wi-Fi has the fastest speed. However, for most IoT smart home products, it's not necessary to have this fast of a speed. The Zigbee and Z-Wave outperform Wi-Fi in terms of battery life. 15,000 hours is the average lifetime for a single Philip Hue light bulb, and 10 hours is the average amount of time it would take for a Wi-Fi connected phone to last before it needs to be recharged. Low power consumption is one of the pros of both Zigbee and Z-Wave. This is important for an IoT product like the Philip Hue bulbs, since you would not want to replace or recharge your light bulbs every 10 or so hours. Wi-Fi typically operates at a 2.4 or 5 GHz broadband. The benefit of Z-Wave is that it's less prone to congestion issues because it operates at a different radio frequency of about 908.42 MHz. Both Zigbee and most Wi-Fi smart home devices communicate over 2.4 GHz, which can cause more traffic congestion in smart home with more devices. Zigbee only works on a wireless personal network, WPAN, and Wi-Fi works on both WPAN and LANs. An interesting discovery is that Zigbee is prone to attacks where the attacker can find out the status of lights in someone's home, which is a privacy concern. Since Zigbee allows smart home devices to communicate with each other, if the Philip Hue bridge is attacked, it can take control of your home network. For example, a Zigbee antenna can be used by the attacker to push one of the bulbs off the network and put malicious code into it. Then, if the user tries to repair their bulb to the Hue app, the malware can be spread to the bulb, then to the bridge, and then take over the rest of your home network.
This is Google Home, and these are some of the use cases for this device. Watching and listening to media, control TV and speakers, planning our day, getting things done, managing tasks, and actually getting factual. We have the Google Nest Hub. The use cases for this product are camera integration, user input hub, watching and listening to media, controlling TV and speakers, planning our day, getting our things done, managing tasks, getting factual answers, and control your home. Some properties of this Nest Hub. include IFTTT integration, Google's OAuth 2.0 APIs that can be used for authentication and authorization, some connectivity protocols, and some user-perceived latency, which is immediate response as expected. This diagram showcases the Google Nest Hub at a glance.
Ring is a smart doorbell which detects movement outside a house and notifies the homeowner when there are guests waiting outside. This device uses NTP, HTTP, HTTPS, and DNS protocols, as well as TCP or UDP protocols for live view video when interacting or monitoring live through Ring's camera.
HTTP or Hypertext Transfer Protocol is the set of rules for transferring files such as text, graphic images, sound, video, and other multimedia files on the World Wide Web. As soon as a web user opens their web browser, the user is directly making use of HTTP. HTTP is an application protocol that runs on top of the TCP IP suite of protocols, the foundation protocols for the Internet. HTTPS is the Secure Sockets Layer, which is the SSL, or Transport Layer Security, TLS, as a sublayer under regular HTTP application layering. HTTPS encrypts and decrypts user HTTP page requests, as well as the pages that are returned by the web server. The use of HTTPS protects against eavesdropping and man-in-the-middle MITM attacks that use HTTPS. TCP or Transmission Control Protocol, a standard defining how to establish and maintain a network conversation through which application programs can exchange data. Works with IP. Web servers use HTTP to set up connection and send the file. TCP program layer waits until all packets have arrived and waits for any retransmissions. It then assembles the packets into a file and redelivers the file to the receiving applications. Devices that use TCP include Alexa, Google Home, and Google Nest Thermostat, including Ring and iRobot. Applications such as VoIP, streaming videos, and gaming rely on user datagram protocol. It reduces latency and jitter. It does not reorder packets or get missing data retransmitted. There is no way of detecting whether applications have completed back and forth communication. Instead of correcting data packets, UDPs discard packets and defers to the application layer for error detection. Devices that use UDP include Google, Alexa, Google Nest, Ring, and iRobot. The domain name system, DNS, is the phone book of the Internet. Humans access information online through domain names like nytimes or espn.com. Web browsers interact through Internet Protocol IP addresses. DNS translates these domain names to IP addresses so browsers can load the Internet sources. They eliminate the need to remember complex alphanumeric IP addresses such as the ones shown here. Moving on to TCP versus UDP comparison. This slide focuses on the comparison between TCP and UDP. Although both of them run on top of IP, there are certain differences between the two protocols that are listed here in this table.
The iRobot Roomba uses a specialized serial protocol called the ROI, which stands for Roomba Open Interface. This enables users to connect with the Roomba through an external port to view the internal workings at an abstracted level. From the user interface interactions, it has a physical layer that uses Wi-Fi certified IEEE 802.11b. IEEE stands for the Institute of Electrical and Electronics Engineers, and this has LAN standards. These protocols are designed to work well with Ethernet and typically carry IP traffic. The range of this IEEE 802.11b protocol is up to 400 meters and has a baud rate of 1 and 2 megabytes per second. The application layer that this ROI protocol uses is a web server HTTP TCP port and has a TCP socket server. The iRobot Roomba 980 is a Wi-Fi connected robotic vacuum cleaner that can be controlled by a mobile app and buttons on the robot. When the ROI protocol is used, there are 5 states that the Roomba can exist in. Sleep mode is essentially when the Roomba is off and will not respond to any commands over the ROI protocol. However, the power button can turn the Roomba into the on state. When the Roomba is on, it is awaiting a start command from the ROI. After a start command has been received, the Roomba is in passive state, where the buttons functions as usual, but there is no control of the robot available. Typically from passive mode, the robot receives a control command and goes into safe mode, which is where the sensors detect a problem such as the robot is picked up or gets stuck. Safe mode can also be reached from full mode, and this full state diagram can be seen on the slide. This is the list of pros and cons for the ROI protocol. The pros of this is that the robot's data remains secure. The cons of using the ROI protocol is that it uses numerous ROI data types and only one command returns data. The data types come in the form of a single byte, 16-bit value represented as 2 bytes, several bits encapsulated in a single byte, and combinations of the previous. This makes it difficult to see the data that is coming back to keep track of the syntax. Also, this protocol is only unique to Roomba. If a user has other iRobot products, such as the robotic lawnmower Terra or robotic mop the Brava, they will not be able to use this protocol to look at data being transferred and debug their device.
Calls in use for the various IoT products that are commonly found in smart homes. Manager hubs like Alexa and Google Home use Zigbee, Z-Wave, DNS, TCP, HTTP, and UDP protocols. Lightning products like Philips uses Zigbee, whereas other IoT products like Roomba, Nest, and Ring use DNS, TCP, HTTP, and UDP to communicate with the respective servers. Thank you for your time and patience, and we would love to address any questions and feedback you may have now.